preciso.
Quando a gente veio com o Brian, né?
Ah, sim, agora já está com cara de casa ocupada, antes era casa vazia. Você viu aqui, ó, série 2, série 3, agora está faltando série 4.
Vai chegar o série 4, já está chegando. Vocês vão botar na parede?
Nós vamos botar no brise inteiro, né? We'll have a brise soleil on the facade, made all of these modules.
But that will be the series 3.
That will be the series 3 to send us the 10
We'll do
kilowatts.
something else with the series 4.
And then we do the series 4 will be
For the
mounted
test site.
on the
Test
ground for utility scale.
Ok. Mas podia botar
A gente vai fazer isso também.
uma evolução.
Eu precisava conseguir um de 45 watts, que era o primeiro. Se você um dia tiver a chance de mandar um bem das antigas lá,
Eu vou falar com o Brian.
aí a gente faz esse negócio da parede.
Tá.
Pode ser? De prender na parede? Não, perfeito. Tem 16 pessoas. Muito bom dia, então, a todos. Sejam todos bem-vindos aqui ao nosso laboratório. Nós vamos dar início, então, a essa sequência de apresentações da First Solar. São os nossos convidados aqui hoje para apresentar esse seminário, né, e a utilização de módulos de filmes finos de teleto de cádmio, simulação com PVSYST e sistemas fotovoltaicos de grande porte, olhando já para tensões de 1.500 volts, que é uma tendência, né, com o objetivo de reduzir custos de usinas fotovoltaicas. Nós temos também as pessoas nos assistindo pela internet, e essa apresentação está sendo gravada, né, então ela vai estar disponível no site do laboratório para depois, para quem quiser assistir. Eu vou passar a palavra logo para a Gabriela, que vai fazer uma apresentação da First Solar, e na sequência para os nossos convidados, né, a Kendra e o Manuel, vão falar então sobre especificamente esses assuntos que eu mencionei. Então, Gabriela, por favor.
Obrigada, Ricardo. Obrigada por nos receber aqui no laboratório. Bom dia a todos que estão aqui presentes. Bom dia aos que estão nos assistindo pela internet. É um prazer estar aqui com vocês hoje, representando a First Solar, para introduzir os meus colegas que vieram diretamente dos Estados Unidos para dividir um pouco do nosso conhecimento aqui com o mercado brasileiro. O nosso objetivo hoje é trazer para os alunos aqui da universidade, para alguns dos nossos parceiros que estão aqui presentes e para empresas interessadas no segmento de energia fotovoltaica em as vantagens tecnológicas que o módulo de filme fino, a partir de teloreto de cádmio, apresenta aqui no território nacional, por ser um território onde temos um clima quente e úmido, onde é muito bem-vindo para a nossa tecnologia. Eu gostaria de avisar que esse material que está aqui na mesa está disponível para vocês. Para o pessoal que está nos assistindo pela internet, se pudessem enviar um e-mail aqui para o e-mail do laboratório com o seu contato, a gente vai disponibilizar tanto as apresentações quanto o material. E também a Kendra, que vai seguir depois dessa apresentação, vai apresentar o Plant Predict, que é uma ferramenta interna desenvolvida pela First Solar, que a gente utiliza para fazer previsão de energia. Ela funciona um pouco diferente do PVSYST, porque ela consegue capturar alguns elementos que não existem hoje no PVSYST, que tornam a previsão de energia um pouco mais precisa, e a gente pode disponibilizar também essa ferramenta em uma versão limitada para usuários que se interessam em fazer previsões com uma ferramenta além do PVSYST. Então, é só mandar um e-mail para mim e eu vou disponibilizar essa ferramenta para vocês. O meu e-mail é gabriela.com.darrochaoliveira@firstsolar.com. Então, quem precisar de acesso à ferramenta do Plant Predict e precisar do material que vai ser distribuído aqui hoje, é só me mandar um e-mail. E para quem tiver perguntas sobre filme fino sobre a First Solar, também podem me mandar um e-mail. Para não atrasar mais aqui as nossas apresentações, eu vou passar a palavra para a Kendra. Mas antes disso, eu só queria ver aqui no pessoal que está no auditório, quantos de vocês são alunos da universidade? Quantos, incluindo os que não são alunos, vêm utilizando ou já utilizaram a ferramenta do PVSYST, são familiar com essa ferramenta? Então, quase todo mundo aqui. Então, vocês vão gostar bastante da apresentação de hoje da Kendra. Vou passar a palavra para ela. Obrigada.
Hello, everyone, and welcome. I'm sure Gabriella gave me a very nice introduction, but unfortunately I didn't understand any of it. I did prepare some materials for today, but unfortunately I was not able to learn Portuguese in a week, so sorry about that. If you have any questions, I think we'll do them at the end, but if you're having trouble understanding me, please indicate that to me as I go. I work with the Prediction and Performance group in San Francisco as a performance engineer. So our group does a lot of modeling work, both looking at how our measured plants are performing compared to the prediction, and then using those differences to improve and develop new models as well. So today, my first presentation will talk a little bit in general about the First Solar technology. And then the second one will go into more detail about modeling specifically in PVSYST or in our internal software Plant Predict. So this first presentation will look first at our Series 4 V2 modules, the latest generation. We'll look at some of the performance characteristics that set our modules apart, such as shading, temperature coefficient, spectrum, and soiling. And we'll finish up by looking at our quality and reliability and our long-term performance, looking at some of our certifications, our performance in the field, as well as how well our energy predictions do in indicating measured performance. So to look at for solar technology, we really have to start at the beginning with our first module produced about 20 years ago now. At that time, thin film was considered to be a low efficiency technology. We were producing modules at 50 watts and about 7% efficiency. Today, the modules coming off of our production line are more than double those amounts, so 115 watts and 16% efficiency. And as I'll talk about a little bit more later, we've been setting world records and continue to expect to do that in the future as well. Here we can see the composition of our first solar thin film device. The basic construction is largely constructed of glass, plastic glass, such as you would find in your windshield of your car, and that's something that we all consider to be a very strong package. If we zoom in on the very thin semiconductor layer here, you can see the cadmium telluride layer. This is about 1/26 the width of a human hair, only about 14 grams per module. And this is produced mainly from the byproducts of copper and zinc refining. Here we have a fun little video of our manufacturing process. Let's see if we can get it to play. There we go. First we have the window layer, cadmium sulfide, deposited by vapor transport deposition, followed by the absorber layer, the cadmium telluride. From here, the module goes into the first of 3 laser scribes. The first you see here isolates our cells, filling with an insulator. The second laser scribe goes through the solar layer here and is filled in with sputter deposition. This is the back contact. And this connects the negative side of one cell to the positive side of the next. And the final isolation of the cells is accomplished with the third laser scribe. Following this, our modules are encapsulated. So first we have the bus tape, then the edge seal, followed by the laminate layer, and finally the back glass. At this point, the modules are sent into a high heat process that laminates the modules. And then before going out into the field, we add the cord plate here, and all of our modules undergo performance testing before being installed. And here you can see all of the layers we just talked about with the flow of electrons through the module. And one of the important things when we're talking about our manufacturing process is that it all takes place under one roof. So in under 2.5 hours, you go from having a piece of glass to having a functional module. This compared to crystalline silicon, where you may have parts of your process contracted out to third parties. You don't have as much control over quality and reliability like we do. And you can see some great examples of our modules right here. We did set a world record this year in terms of cell efficiency at 21.5%. This was certified at the Newport lab. And if we look at the trends in efficiency in the last few years here, you can see that First Solar has been setting records at a very steep pace. So in the last 4 years, we've seen an increase in efficiency of over 4%. So now in 2015, we're at 21.5%, which is better than the best multicrystalline silicon record at 20.8. And one thing I like to point out here is that multicrystalline silicon did set a record this year, but it was the first one in 10 years and only showed an improvement of 0.4%. Here we see the other world record that we set this year, which was for our module, which was certified at 18.6%. Before you start looking, no, none of us are in this picture. This is our very smart module team in Perrysburg, Ohio. And this module does represent some of the improvements that were made to get our world record cell, but not all of them. We expect this number to go up as we integrate those processes over the next couple of years. And in terms of aperture area, this 18.6% efficiency puts us slightly behind the best PERC cell at 19.14%. But what we really care about when putting modules out in the field is not the active area, but the total area, including edge delete and things like that. So if we use that metric, we are ahead at 18.2% over 17.7%. And we attribute a lot of this quick success to our investment in research and development. Here you can see many of the different companies and their investments over the last few years, where First Solar in yellow and red here comes out on top. We've invested $134 million in 2013, and we expect that number to be the same or more in the coming years as well. Of course, efficiency is not the only thing that we care about when looking at performance of a PV plant in the field. Here we can see our energy density roadmap, which shows that we continue to pull ahead of crystalline silicon in the coming years. We can see in terms of efficiency, in Q1 of this year, we might have had a slight efficiency deficit, but we expect to close the gap in terms of efficiency by the end of Q4 2016. And continue increasing that gap. But as I will talk about next, we have a lot of different characteristics to our modules, such as temperature coefficient, spectral shift, and true tracking that give us other benefits in terms of energy density. So here we are, differentiated performance. First, we can talk about the shading characteristics of our modules. When you install our modules in landscape, they are robust against shading. This is due to the way that they're internally wired in a serpentine pattern rather than in connected rows of series cells. So this causes our shading loss and our power loss to be linear. So if you have a 10% shading loss, we expect a 10% power loss. This is compared to crystalline silicon, where it's not a linear effect. You may have 10% shading and a 30% output power loss. This allows us to minimize early and late evening energy loss while allowing us to pack our rows closer together. This gives us a particular benefit when we look at our tracker technology. With this linear shading response, we don't need to backtrack like crystalline silicon modules do. Traditionally, they point away from the sun early in the morning and late in the evening in order to avoid shading, which causes a greater power loss for them and can also cause bypass diode failures. So instead of backtracking, we do true tracking, where we continue to follow the sun until it sets in the sky. And on the right here, you can see some experimental results from one of our white papers, where we actually had 3 systems where we turned backtracking on and off to see if we actually got the power increase we expected. And if we just choose one of these, the one on the bottom here, the median system in black is backtracking, and the other 2 are true tracking. You can definitely see that we have a power advantage with the true tracking. We also have an advantage in terms of temperature coefficient. Our newest module technology has a value of 0.29% per degree C, and this means that anytime our module temperature is above 25 degrees, we see an advantage in terms of performance for the same nameplate. Especially if you look at typical field operating conditions, where module temperatures could be in the range of 40 to 65 C. This will give us quite a big advantage in climates such as Brazil, where it's very hot. Here we have a fun animation. We can see a typical day in a hot climate, where we have the ambient and module temperatures shown on the left, and then we can see the power for a First Solar and a crystalline silicon example compared above. So as the sun comes up, we see the temperature start to increase. At the middle of the day, when the temperature is reaching its peak, so also is our energy production, which causes us to get 11.3% more peak power in this case. And by the end of the day, we can see that we accumulated 9% more energy.
This is with the same nameplate power?
Correct. Here's another way to look at it. For a typical hot desert climate, we can look at the percent of total energy produced at each of these back of module temperatures. What it shows is that anytime we're above 25 degrees C, we have an advantage, and this is happening in this climate 90% of the time. And when we are above 45 degrees C, we have over a 5% yield advantage, which is happening over 60% of the time. I'm going to talk a little bit about spectral shift, but I will be going into more detail later in the second, more technical presentation. The basic concept of spectral shift is that as we increase the amount of precipitable water in our atmosphere, we see this greater amount of energy for the same nameplate. And this has to do with the absorption bands for water that you see here in our spectral irradiance curve. As these absorption bands increase, which means that we have less irradiance at these particular wavelengths, this affects the crystalline silicon. You can see the spectral response curve here, where it is included, and it does not affect the cadmium telluride curve as much, which you can see here excludes these larger absorption bands. Here we can see what the spectral shift advantage looks like in Brazil. In general, we see that the values are between 4 and 6% advantage. If we add in the thermal advantage here, we see about 1% more than that, so between 5 and over 7% advantage. It's also very important to look at soiling no matter what climate you're looking at. It's very important to understanding performance. You can see here one of our soiling monitoring stations that we set up hopefully at least 1 year prior to construction to get an idea of the local conditions. One module will be cleaned and one will remain dirty, and we compare the short circuit current in order to quantify the amount of soiling. Without this data, currently we don't have any of these set up in Brazil. We hope to have them in the future. You can get an idea of the amount of soiling by looking at the climate in the region and the amount of rainfall that's expected. Just looking at the climate map, the Köppen-Geiger climate map, we see that a lot of Brazil is obviously tropical. This means more rain and we expect less soiling. Other areas that are subtropical, you can see in green here, or semi-arid in orange, we do expect these rates to be higher. One advantage that our modules do have is that they are frameless, as you can see here. This means that when rain or dew even is on our modules and it's rolling off, it can carry the dust with it off the edge without being caught in the frame. Of course, just looking at a climate map can be very limiting. Here we see a case in the desert US Southwest where it's classified the same as a desert in Saudi Arabia. Here we see a 1% per month rate in the desert Southwest of the United States and a much greater 14% per month rate in Saudi Arabia. And it's also very difficult to tell by just visually looking at a module how much soiling is on it. Here we can see an example where we have increased rates of soiling over time, but visually it would be very difficult to tell. Sometimes in our group we even have a little competition where we'll send around a picture and actually guess, and it's very difficult to come up with the correct number just visually. So finally, we will look at reliability and long-term performance. Traditionally, there have been IEC tests, including thermal cycling, damp heat, and humidity freeze cycling that were used to characterize the performance of a module. These days, we consider these to be representative of infant mortality, so what's going to happen when you initially put out the module in the field, but what we really care about is how it's going to last through the power plant lifetime, 20, 25 years. So tests that we use to quantify this are the Thresher, long-term sequential, and Atlas 25 plus tests. Here on the left, you can see a depiction of the long-term sequential test where a single set of modules will be put in series through each of these tests. The Thresher test, or conventional extended testing, is shown on the right, where different groups of modules will be put through each of these tests individually, but it will be at higher cycling or more hours. Here you can see the results from some of these tests for our Series 3 black modules. On the left, we see extended thermal cycling, where we're moving from negative 40 C all the way up to 85 C and back, where traditionally the IEC limit was only 200 cycles. You can see here that even out to 1,000 cycles, we don't see a significant drop in our power performance. On the right, we see the extended damp heat test, where it will be exposed to high temperature and high humidity for a certain number of hours. The IEC limit is traditionally 1,000 hours, and you can see even out to 6,500 hours, we are still well above the IEC limit of 10% power loss. And this really gives us confidence that even under harsh conditions, our modules will perform as expected. They will perform well and last the test of time. And here you can see our brag sheet. This is all of the different certifications that our modules have passed. We are 1500 volt certified, one of the first module manufacturers in the world. We did pass external Thresher certification, as I mentioned, with less than 5% power drop. We passed the long-term sequential test as the first thin film module and also one of only 5 modules in the world. We also passed the Atlas 25 Plus test, which is meant to characterize real-world performance. It's outdoor testing for 12 months, including exposure to salt corrosion, high humidity, things like that. We are one of only 4 modules in the world to pass that test. We're also certified PID-free and desert sand resistant.
How long do you run this qualification or certification? How long does it take in the development of a new series?
That's a good question. I'm not sure off the top of my head, but as I mentioned, the Atlas 25 Plus test being an outdoor test is probably the one that takes the longest because it does include 12 months of field exposure. And here you can see all of the different tests that we have passed, and you can see that we are the only module manufacturer to have passed all of these tests. Of course, even though this indicates that we do have high reliability, we are not one of the high-price manufacturers on the market, so we're really offering a good value and ensuring that you will have quality into the future as well. And all of this reliability is facilitated by our extended equipment that we have access to in our labs in Perrysburg, Ohio. You can see some of those listed here. The thing that I find really interesting about this slide in particular is in the upper left here, looking at how many modules we test every year. To put it in perspective, we will test to destruction over 8 megawatts of modules every year from our production line of 3 gigawatts. We expect to increase that to 5 gigawatts in the next 3 years, but you can imagine that 8 megawatts of modules is quite a few. It's bigger than a lot of solar power plants you would find here. Besides testing in the lab, we need to look at real-world outdoor performance as well, and to do this we have test sites around the world. A couple in the United States, Malaysia, Chile, India, and the Philippines, and we hope in the near future to have one right here in Brazil as well. This allows us to look at our technology's performance compared to our competitors, evaluate new technologies, and compare it to old technologies as well, and look at any reliability issues that may come up. And not only do we have testing that we do ourselves, but we also perform well in independent tests. Here you can see an example of a 4-year-old test that's being conducted in Miami, Florida, where we are compared side by side with multicrystalline silicon, SIGs, amorphous silicon, other thin film technologies as well. And in terms of lifetime normalized specific yields, we have been outperforming all of these other technologies. One more thing that we can show that shows our confidence in our performance over the lifetime of a power plant is this particular test. It's very unique at NREL, the National Renewable Energy Laboratory in Denver, Colorado. We've had modules out there for 19 years. You can see the plot on the left, and also a 13-year study on the right, where we've been measuring the degradation rate over time. And you can see in both cases here, we're below the 0.5% per year threshold that we specify on our specification sheets. This is comparable to other established PV technologies and indicates that we're not expecting any wear-out mechanism, any problems that will affect the performance into the future. One of the things that my group is most proud of is our benchmarking program, where we compare measured performance to actual predicted performance. In this case, we've looked at over 1 gigawatt of capacity spread over 20 different sites and 4 countries. The oldest of these sites is now about 5 years old. And here you can see a histogram of model error for these 20 different sites. So we're looking at error at the energy meter. You can see on average we are predicting within 0.12% with a standard deviation of 1.91%. This gives us confidence that not only are our plants performing well, but we can tell you exactly how they will perform. And with that, I think that's the end of this first piece of the presentation, and I'm happy to take any questions.
Hi, Kendra. One issue in Brazil is for wind parks. That we could share the infrastructure of these wind parks with solar plants.
Right.
For some of the sites, we could have high wind peaks that could lead to a non-homogeneous soiling into the model.
Okay.
My question is, if you have any site that you also have this kind of situation, and if the approach to assess the soiling losses, comparing the short-circuit current of a dirty and a clean model, should be the best approach to assess this kind of losses?
Definitely. We definitely have sites that have high wind, but we don't necessarily see an increase in soiling as a result. Perhaps at these wind farms you would see increased turbulence or something that would cause greater soiling. As you see, we have some plants in places like Saudi Arabia where we have very high soiling rates, like 14%, something like that. And in those cases, we do have the option to clean modules. I'm not sure this would be the right application, but it is an option if it really is a problem. In that case, we use a dry brush technology where it's pushed across the modules. But I think really more studies will have to be done in order to determine what soiling rates are like in these areas. I would be very interested to see those results. And we do generally use the comparison of two modules side by side because soiling can be different depending on the surface that you're using, things like that. It's a very easy way to take out some of the confounding variables in a test like that. We are developing a new way to look at soiling as well, where we can just look at a much smaller piece and sorry, we can look at a much smaller piece and move a filter across the top that is soiled. But that's still in the development stage at this point.
Quem tem mais perguntas, a gente vai pedir para falar sempre no microfone, tá? Que está sendo gravada a apresentação.
É o Martin da VEG. I saw in the power range of your models that you are going to 100 something watt per module. So
Yep.
you have quite small modules.
Correct?
This is different than with polycrystalline modules in the market. Do you see to increase the power range with your technology, or will you stay with this 120 watts?
As we move forward in production, as our efficiency increases and our area stays the same, we do expect our wattage to continue to go up. I believe the modules that we're doing initial testing on are, 120, 125 watts already.
This brings additional wiring with it because you have the wire to the lower wattage. Is this a main concern in your technology?
To answer that very question, we will be moving in our next series some years out yet to what we're calling a module assembly, where we'll have 3 modules mounted together on a back rail. So you can imagine that functionally this will be very similar to a larger, higher wattage module from a different manufacturer.
Mais perguntas? Os alunos têm que fazer perguntas. Eu encomendei uma pergunta de cada aluno. Vão pensando aí.
Oh, hello. About the lifetime of the module,
Sure.
do you have any tests that could imply that the module would have a bigger lifetime of the 25 years? Any kind of certification that the module would last for about 35 years?
I am not sure specifically, but just looking at the results as I showed from the IEC extended testing, where it shows minimal output drop even over extended cycling or extended hours at extreme conditions, I think this could indicate a lifetime that would go beyond that, but of course it will still be experiencing that degradation rate, so your power output will decrease slightly from year to year.
Thank you.
I also have a question on the lifetime and on the annual degradation.
Sure.
You showed the 19 years degradation. Can you go back to that slide, that one?
Yep.
Less than 0.3% per year. But you've been running now a number of utility scale plants.
Yeah.
And do you see that same kind of trend of degradation rates in your large PV plants?
Yes, we
and
do.
how long? Which one is how old is the oldest of these plants for where you have data?
Right. So the oldest plants we have data for now is around 5 years old, and this doesn't give us a lot of time to look at degradation rates, where it can obviously be a very noisy metric when looking at field data. But initial results, if you group many sites together, do show that we're in line with this number in our utility scale plants.
Thank you. Mais perguntas? Ok, então a gente vai encerrar essa primeira parte. So, would you like to go right on the next
Sure.
topic?
We can?
Okay.
So now we're going to get down into the nitty-gritty, the modeling piece. So for you nerds out there, this will hopefully be the part that you enjoy more. We'll start by looking at general guidelines for PVSYST modeling. First, looking at choice of a meteorological file, then following up by looking at the project parameters that should be used when modeling for solar CAD/TEL technology compared to what is typically used for crystalline silicon. So we'll look specifically at thermal losses, module quality and mismatch, soiling. We'll go into more detail this time on spectral shift. We'll look at incidence angle modifier and tracking. Following that, we will look at a specific example comparing cadmium telluride and crystalline silicon performance here in Brazil. And finally, I will talk a little bit about our indicative energy model, which is available to all of you if you are interested, in order to do simple, easier than PVSYST simulations to get more of a back-of-the-envelope calculation for these kinds of analyses in the future. So in this case, I have been using version 6.3.2 of PVSYST, using PVSYST because it is the standard in the industry today. Just one quick note that the versions shown here, 2.7 through 2.9, are affected by a bug, so please don't use these when modeling our technology. Other tools that we find useful when performing modeling is, of course, Google Earth, looking at siting options, things like that. Also geographical things that we might need to take into consideration, as well as using Meadow, of course, for looking at different weather files. We do have an energy prediction bundle that does give detailed guidance on a lot of the things that I'm talking about today. If you're interested in looking at these documents, please ask for them. We're happy to give them to you. So first, looking at choosing a Meadow file. Of course, we want to be using the highest resolution available. We all know that in PVSYST that there are options to just use the data that is included there, but that is only a monthly weather file that is then broken down somehow into an hourly file, and we don't expect those to be very accurate. We want to use data that is typical mean years, so not representing extremes. This usually means that it's satellite data collected over several years and averaged together. We'd rather look at this than a raw time series that's only a year long. If you are going to go out and buy a weather file, if you're going to model our technology, you will need either precipitable water data included or relative humidity and ambient temperature for the spectral shift component of the modeling. In terms of choosing a location for your weather file, you want to make sure that it's comparable in altitude to the location where your project will be. Things like mountain ranges in between your weather file and your project site could definitely alter the local weather patterns. And when you're using a tool like Meadow, where it uses several different satellite readings and interpolates to your particular location, you want to be careful, especially if you're using somewhere maybe near the coast, where it might be using a coastal satellite data and interpolating with inland, where it can definitely pull down your irradiance. Here you can see some of the weather data sources that we regularly use. A lot of the ones listed here on the left are only United States data. Here in Brazil, I think the ones that will be most important will be Meadow as well as GeoModel Solar, where you can definitely get the local weather data you need, as well as hiring ground proofing sorts of things as well. Now here we will go specifically in some of the parameter assumptions for cadmium telluride versus crystalline silicon. Here you see the table summarized, but we'll be stepping through each of these in order, starting with thermal modeling coefficients. Traditionally in PVSYST, the defaults for a utility scale fixed tilt system are 29 and 0. And these are for the constant loss factor and the wind loss factor. These you can think of as the free and forced convection terms if you're familiar with heat transfer. However, we weren't happy with the results that we were getting by using these defaults. So what we did was look at our measure data at several different sites. Here on the left, you can see the average temperature residual, so the modeled minus the measured value as a function of the plane of array irradiance. And here in blue, we see how this profile looks when using the defaults, and in green, we see the profile when using our guidance of 30.7. And here you can see that we get much closer to a residual of 0 with the green line, the 30.7 value, without passing it. So the fact that we don't go past the 0 line means that we are in general, sure, thank you. It means in general that we are still more conservative. On the right, you can see how we arrived at this number. We looked at 4 different climate types, including hot and cold in North America and a couple different sites in Europe as well. And here you can see the thermal loss coefficient as a function of the temperature error again. And each of these sites you can see the optimization, where the best value, of course, would be the lowest point in the trough. And what we ended up choosing here was the most conservative value, which is the lowest thermal loss coefficient of 30.7 for the hot climate in North America. Of course, if you have a higher thermal loss coefficient, you will have more cooling, and this will bring your module panel temperature down. So you can see why a lower thermal loss coefficient is therefore more conservative. Looking at crystalline silicon technology, they have not done any of these studies, so we recommend that you still use 29 and 0, which are the defaults in PVSYST, because these thermal parameters can be very technology specific. Depends on the profile of the module, the way it's mounted, everything like that. Looking at module quality and mismatch, we have traditionally used a value of 1% for module quality. This is actually representative of what we think of as DC health. So when going out into the field, traditionally we have seen that about 1% of strings were disconnected, leading to about a 1% loss. We hope to bring this value down in the future by looking at more recent power plant data, but in this case we have used 1%, and we don't expect crystalline silicon to be any different, so we have matched those to make our simulations more comparable. Same goes for power loss at MPP, again, 1%. Crystalline silicon, as you all know, also has light-induced degradation, or LID. This typically means that they have a 2% penalty when being modeled. We can look again at soiling here briefly. Again, you can get an idea of what the soiling rates may be by looking at climate type, but it can be very local depending on agriculture nearby or local weather patterns. So it's very important, if possible, to get real measured data on the ground. In this case, we've assumed that cadmium telluride and crystalline silicon will have the same amount of soiling. And one important note is that in PVSYST, when modeling cadmium telluride, you will include the spectral shift. And now we get into the nitty-gritty of spectral shift. We have published repeatedly on this topic, and we will be publishing again on it in the near future. And we've demonstrated that you really need to include this in modeling our technology to match expected performance. It's not included currently in PVSYST. It's on their list of things to do, but we haven't managed to bully them into doing it quite yet. Here you can see on the right the PPI, which is Power Performance Index, an indication of how well the modules are doing, in 2 test arrays in Mesa, Arizona. And you can see the spectral shift plotted on top of it in red. You can see as our time trend continues that we see that these 2 metrics match very well. So, why does spectrum affect our modules? Here you can see the spectral irradiance, the ASTM G173 standard spectrum. May look familiar from physics class back in the day. This is what we expect to hit the Earth after going through the atmosphere, and it is a standard spectrum, so this is specified at 1,000 watts per meter squared, 25 degrees C, and 1.42 centimeters of precipitable water content. Of course, when we're looking at PV, we generally don't use this entire spectrum, so we're going to zoom in on this region here. So here we're zoomed in, and most of us are familiar with the fact that our eyes only see certain wavelengths out of this full spectrum, called the visible spectrum, from violet to red, and that's from about 400 to 700 nanometers. Similarly, our modules only see certain wavelengths of this full spectrum, for solar out to about 900 nanometers, and crystalline silicon out to about 1250. Please note here that the quantum efficiency curves shown here aren't necessarily related to the efficiency of the panel. That is related to the number of electrons that are produced from incoming photons, or the spectral response. The QE curve shown here is just representative of the percentage of photons that are actually absorbed. So if we compare this to a broadband pyranometer, broadband meaning that it reads a broad band of different wavelengths out to about 2800 nanometers in a typical Kip and Zonin model. Cadmium telluride only cares about wavelengths out to 900 nanometers, and crystalline silicon sees wavelengths all the way out to 1250. Of course, again, this is not necessarily related to efficiency. That is more a function of the module material, which is related then to its band gap. And why we care about the width of these absorption bands that each of these modules sees are these water absorption bands shown here, where the largest of these are seen by the crystalline silicon module, but not by the cadmium telluride module here. This means that when the atmosphere has a high precipitable water content, these absorption bands will increase, and we will still have the same number of useful wavelengths, where crystalline silicon will have fewer. I think it's most helpful to look at this in terms of an example, so we'll show that here. Here we see the standard G173 spectrum again with our two QE curves plotted on top. And at the bottom we can see our broadband pyranometer reading, which we know at standard spectrum is 1,000 watts per meter squared. And in this case, to make it simple, we'll look at two side-by-side modules, one cadmium telluride and one crystalline silicon, where they're both at 100 watts. Now, we're going to increase the precipitable water content while keeping the total amount of irradiance the same. So we're thinking about the total irradiance as the area under the full curve all the way out to 2,800 nanometers for the broadband pyranometer. Here you can see our precipitable water content is now 4.5. We've picked a very extreme value so you can visually see the shift here, but we're still at 1,000 watts per meter squared. So you can imagine for this curve to have the same area underneath as our previous example. If these water absorption bands are increasing here, the rest of this curve moves up slightly. So under our cadmium telluride curve here, we see a gain in terms of the useful irradiance. If we're looking at crystalline silicon, overall we see a little bit of a gain, but it has this large loss due to these absorption bands. So if we look at the power output of each of these as calculated using the SMARTS model, we're looking at a 4.7 watt increase for cadmium telluride and a 1.2 watt increase for crystalline silicon. Conversely, if we have an extremely low value of precipitable water, in this case 0.45, if we're holding our total amount of irradiance the same, we see these water absorption bands increase a little bit in the upwards direction. This means that the rest of this curve comes down a little bit. So most areas under the cadmium telluride curve see less useful irradiance, and the wavelengths included under the crystalline silicon curve see more because of these absorption bands here. So here, in terms of power, we're looking at a wattage of 96.7 watts for cadmium telluride and 98 for crystalline silicon. Of course, we want to look at what are actually realistic values for precipitable water in different locations. Here we can see precipitable water for Mumbai in orange, Phoenix in green, and Berlin in blue as a function of the month of the year, and the corresponding spectral shift value for each of these climates shown on the right. In general, precipitable water is equivalent to a high spectral advantage for our technology, and it occurs in climates with high relative humidity and ambient temperature, so locations like Mumbai. And you also notice that the highest gain in terms of precipitable water, and therefore spectral shift, occurs in months during the summer when we are producing more energy. This means on an annual basis we see a greater gain. If we look at crystalline silicon, Sandia, a National Renewable Energy Laboratory in the United States, has shown that spectral shift is largely a function of air mass for this technology. So here you can see the air mass for these same three locations plotted here, and the spectral shift on the right. So high air mass is equivalent to higher spectral shift for crystalline silicon, where the highest annual air mass occurs at locations that have higher latitudes. This is also a function slightly of elevation, but latitude is the larger adjuster. And we notice that the highest gains are in the winter, which means that solar plants are producing less energy when there's more gain for this technology. So on an annual basis, the gain is much smaller. And you can see just in terms of the magnitudes of the shift due to air mass, it's much smaller than the ones that we saw for cadmium telluride due to precipitable water. And here we can see the correlations side by side, where on the left we see the cadmium telluride series 4 correlation. This was calculated empirically from 13 different sites using the SMARTS model. We have extended publication on this concept if you're interested. But again, we see that higher precipitable water content is equivalent to a higher spectral shift. On the right, we see crystalline silicon, where the Sandia array performance model computes it as a function of air mass. And you can see again, higher air mass, higher spectral shift. Moving on from spectral shift, we can look finally at tracking. So which parameters should you use? You should generally use whatever the tracker that you're using specifies. So if your minimum tilt angle is -60, as for this example with the next tracker technology, that's what you should use. And again, if you're using for solar cadmium telluride modules with a linear power loss, true tracking is much better than backtracking. So you should definitely uncheck the box in PVSYST. So now we'll look at a specific example in Brazil. Here I've been instructed how to say this, so I hopefully don't get it wrong. Macaúbas, Brazil, was chosen for this example. We used a Meadow file, TMY3, typical mean year data. We have a fixed energy target that we chose as an example of 50.3 gigawatt hours with tracking technology, where we're using NextTracker with limits of -60 to 60, site azimuth of 0, and overall soiling rate for both technologies is assumed at 1%. Here you can see the system design, starting with the module. We have our Series 4-2 module at 115 watts. For comparison, we used one of the ones we've been seeing in competitive bids, the Yingli 315 watt modules. Of course, due to their different characteristics, we'll see a different number of modules in series. In this case, we chose the 1 megawatt GE inverter that we have partnered with, and then this is 1500 volts. And then for the crystalline silicon, we've used the 1000 volt 800 CP US inverter. In terms of number of inverters per PCS, we choose 3 for our GE inverters and 2 for crystalline silicon. And then we have to multiply the output of the inverter that we get from PVSYST by 8 for CdTe and 15 for crystalline silicon to match our DC and AC capacity output at 27 megawatts DC roughly and 24 megawatts AC. Of course, we can't have partial strings or things like that, so they're not exactly the same, but we can see that if anything, our crystalline silicon has the slight advantage here in terms of capacity. And this gives us a DC-AC ratio of around 1.1%. We also made sure to match our ground coverage ratio, which is defined as the collector bandwidth, or the height of the active technology divided by the row spacing. In this case, our ground coverage ratio, or GCR, is about 44%. And here you can see the numbers that we calculated for spectral shift. In the case of cadmium telluride, we have a very large gain in climates like Brazil, as we discussed. Here we see it's 3.9%, and crystalline silicon actually has a slight disadvantage here with a loss of about 1% annually. And if I can get this to work, I'm hoping to show you guys how we calculate these numbers easily. This is one of the things that is included in our energy prediction bundle, and it helps you not only calculate spectral shift, but know exactly what values you should be plugging into PVSYST. So here we open this spreadsheet and we see that we can choose product type, where all of our inputs are in blue. So in Brazil, on the line that we are going to be starting here, we can be sure that this is the one that we will want to select. You can also select model method. Usually we use precipitable water, but if you don't have that data available, you can also switch to using relative humidity and temperature. And then here we've assumed that our DC health number, or our module quality, is 1%, and you'll see how that comes into play in a second here. If I go over to the weather file that we used, all I have to do is take our GHI column here. I'm going to copy that whole thing and paste it into the blue here for GHI. And then also the precipitable water column, which will be way over here. There it is. And please note that precipitable water is not equivalent to rainfall. It is a measure of water that's in the air, not the annual amount of rain that falls from the sky. So you can see as soon as we plug that in here, we see monthly spectral values have been calculated. At this point, we can also plug in our monthly soiling value, which in this case I have assumed is 1% every month. And you can see the next column here adds these two numbers together. And at this point, we realize we have a problem because all of these numbers are negative, and PVSYST will not allow us to put in negative soiling numbers. And that's where this module quality number comes in here. Since it has a very similar effect, it's basically limiting the amount of irradiance that reaches the panel. We can actually subtract that number from our module quality. In this case, we subtract 3.3%. And we can use negative 2.3% as our module quality, where we are allowed to put in a negative value, and then add what we subtracted here to our soiling values, as you can see here, in order to model this accurately. So if you do open the spreadsheet and use it, what you really need to remember is how to enter your different data columns, and then that you need to input what is in green. So your new module quality, and then your monthly soiling numbers. Okay, so let's move on to looking at the results here. Here you can see our firm energy number plotted, as well as the upper limit and the lower limit. We have tried to design our CAD-TEL system such that we meet the first year energy at the very upper limit. So we're producing the maximum amount of power without having the penalties for going above the upper limit. And you can see in this case that the crystalline silicon is starting well below, and it decreases at the same amount every year because we've assumed the same degradation rate. So the takeaway here is that for the same capacity as told here, we produce 6.8% more energy than crystalline silicon. And if we want to look at why that is, we can look at the PVSYST losses as reported here. So if we look at transposition on POA, so how much sunlight is actually reaching our modules, we see a benefit from true tracking of 2.7%. If we look at the near shading, so with true tracking we expect more shading, and we see that penalty here of 2.3%. We also, due to true tracking, have a slightly different IAM profile at the beginning and the end of the day, in addition to having a different IAM profile specified in our module file. So at the beginning and end of the day, we are facing towards the sun rather than slightly away at a more oblique angle, which gives us also a slight benefit here of 0.5%. So altogether, if you add up 3 is 3, it gives you an idea of the benefit that we get due to true tracking in this case, which is just about 1%. We also see the benefit due to our lower temperature coefficient of 1.8% in this case, spectral shift of 4.9%, crystalline silicon sees the LID deficit of 2%. We did choose different inverters because of the different voltages of the system. We get a slight negative loss from this, so 0.4% less. And of course, we are producing a lot more DC energy due to these benefits that I've described. So we do see more inverter clipping of about 1.7% that's docked from our advantage, essentially. So overall, we see where all of these differences come from. And of course, we can increase our DC capacity of our crystalline silicon system in order to match that first-year target. However, to do that, we have to add 2.25 megawatts, or 8.3% more capacity. Of course, we won't be charging you 8.3% more for our technology. Finally, I'm going to speak a little bit about our indicative energy model. Essentially what this is a simple scaled back version of our internal software that is known as Plant Predict. The reason we have this internal software is because we're not content with what PVSYST offers us. So in Plant Predict, we can look at sub-hourly timescales. So if you want to look at minute data, you can do that. We can model our spectral shift. We can develop and test new algorithms. And it also has a lot more detail in terms of post-inverter losses. So everything from medium and high voltage transformers to transmission losses and everything in between. And hopefully someday this will be a commercial competitor of PVSYST, but in the meantime, we have this available for free to our customers. Again, it's a scaled back version that allows you to do many simulations very quickly without all the fuss involved in PVSYST. Here we can see what the different inputs to the model are. We do have the full Plant Predict set of algorithms behind this, but all the parameters are defaulted, such as temperature coefficient. It has all the module information in there already, things like that. You can easily select a Meadow file here. I'll show you what that looks like in a second. You can choose your AC capacity, tracker, or fixed tilt, whether you're looking at for solar modules or one of our competitors, row spacing, inverter, azimuth, DC-AC ratio. You can input a monthly soiling profile if you would like, module wattage, and array count to look at the number of rows and the shading effects. Here you see also you can include a high voltage transformer and specify a plant output limit and power factor. Here you can see the weather selection tool, where it will come up with a map based on your input location. It will search within a 25-mile radius for any weather files that are already in our database. So in this case, there was already one for Rio. If there isn't one already, you have the option to pull weather data directly from our Meadow database. So once you've set up your simulation, it's very easy to copy a simulation and just change one variable or two as you prefer. I think in this case I was looking at different DC-AC ratios for a fixed case in Honduras. And all of these simulations I probably created and ran within 5 or 10 minutes at the very most, which for those of you that have used PVSYST before know that that's quite a bit more time involved. And once I've done this, what I can do is check all of these boxes and click Compare Results. And what we see as an output in Excel is a very useful side-by-side comparison of all these simulations. We see all the different project parameters side by side. We can look at the first year net energy production, specific yield, things like that. We have all the same loss factors as you would find in PVSYST here, and then also an 8760 time series hourly output. And we have run some comparable simulations both in this tool and in PVSYST, and we've seen very good agreement so far. So if you're interested, please let us know and we can set it up an account for you to test it out. And with that, I'll take any questions you might have.
Hi, my name is Ernst. The Metenorm database is not valid Brazil. Why not use the Suera database?
I'm sorry, I don't think I caught that.
The question he was asking is one that we will ask you a lot about. There is a Brazilian solar atlas of a project called Solar and Wind Energy Resource Assessment Project,
Okay.
where we have a 15 now year database that is validated for Brazil. And we know
Okay.
that Meteornorm is not validated. They just have satellite data and it is not validated. The question is why you're using Meteornorm instead of other databases that are available.
Typically when simulating, it obviously depends on the level of detail that you need. In this case, if I'm just doing an indicative assessment, I am not going to care as much about 2% difference in one direction or the other. If I'm comparing two technologies, what I care about is the relative difference. Of course, you want to use the most accurate weather data that you do have available. Typically for new projects, we will put out prospecting stations where it will be measuring not only soiling, but also irradiance and things like that. So we are ground truthing that satellite data.
I'm Daniel from VEG. I have a question about the water, and so but later you showed that it's not so clear for me. In dry weathers and hot, so for these modules doesn't show so much advantage. It show bigger advantage when you have a hot and humid climate. That's right.
Right. Yep.
Okay. I think that our main solar in Brazil is in the northeast. We have some dry weather. No, it was just a question. And I have another one. When you talk about the tracking system, that you show you use a real tracking, I would say, that you admit some shading instead of putting no shading but longer space. You have a slide that shows very well. I understood that with your cadmium tellurite, it's better to have a slight shade than to not have a direct position to the sun.
Right.
Yeah, it's because it's linear, or why do you get that? We couldn't do it with like polycrystalline.
Okay. So first on your question with looking at module performance in a dry region, it will definitely depend on how dry it is, and of course, if it's seasonal, that will affect it as well. You can see here, this was a very extreme example of 0.45, but anytime we are above the ASTM standard precipitable water of 1.42, we will see this advantage. So it's definitely going to depend. We don't see levels as low as the example shown here in regions other than, say, like the Atacama Desert or something. So it will depend, but in general, most of the places that we've been simulating at least have seasonal rainfall, which is equivalent, roughly. It can be correlated with the amount of water in the atmosphere. So we will see some sort of gain, or at least we won't see as much loss as crystalline silicon will. And then if we move on to the shading, I think actually in my other presentation I have a better picture. So, excuse me, I'm not an electrical engineer, but what I understand is that this advantage is due to the way that our modules are wired internally. So if you shade our modules in landscape orientation, since they are wired in a serpentine pattern like this, we're not basically shading one cell of each series connection. So this is why we have this more robust shading profile, and most mono and polycrystalline are all connected such that you will have a nonlinear shading loss.
Mais perguntas? Enquanto vocês pensam, eu tenho algumas perguntas. Can we go to slide 26, please?
There we go. This one?
Yes.
Okay.
So your settings for PVSYST, this is settings for PVSYST, right?
Correct.
So row spacing 4 and nearly 5 meters, 4.5 meters. This row spacing, how are you determining the row spacing? Based on what kind of shadowing tolerance?
Right. So in this example, I tried to stick as closely to example EPRs that we've been seeing coming from Brazil. And in this case, this is very comparable to what we've been seeing. So 18 feet, 4.11 meters for our technology, and then, of course, slightly larger for crystalline silicon to match the ground coverage ratio.
Okay, and the spectral shift is based on input data from PVSYST itself.
From our Meadow norm weather file. So you saw me pull up the example where I was copying GHI and precipitable water from my hourly TMY3 file. So that's where this number comes from. And then that file also includes air mass, which I plugged into the Sandia array performance model in order to get this number here.
Okay, and system voltage is all 1500 volts in each
It
case.
was 1500 volts for the cadmium telluride and 1000 volts for the crystalline silicon.
Okay.
And I also do have this example in PVSYST. If you're interested in looking at the project file, I'd be happy to share that.
And how about the DC-AC ratio? Why are you using just 10% or 11, 13%? People
Again,
here are going more towards 20% sometimes.
Yeah, and of course, as the DC-AC ratio goes up, we'll have more of, we won't have quite as much benefit as that extra energy is clipped at the inverter. But I chose this one specifically because we have seen from other EPCs, developers, we've seen similar DC-AC ratios.
And have you run for these two examples what the PV system total cost would be?
I think Miguel might go into that a little bit later. I believe he has an example. Being on our technical team, I'm pretty insulated from the business money side, so he's the guy for that question.
Okay, the question, Miguel, was for those two 27 megawatt power plants, what is the expected CAPEX for each one of them? But if you're going to go into that later, you can leave it for later.
I have some information.
Okay. Thank you. Perguntas dos meus alunos.
Hi. It is interesting to show other results with also to other thin film technologies beyond the crystalline silicon or not?
Comparing our technology to other thin film. In general, you won't see the same large advantage because of our increased efficiency over other comparable technologies. And of course, we're selling our modules here, so we could show an advantage over thin film, but generally our main competitors are the polycrystalline silicon, where they have similar efficiencies, but slightly less cost, or similar cost.
I think in the next slide you have your inputs for soiling.
Oh, I just used 1% every month.
Yeah, we are seeing here in some of our projects soiling rates which are much higher than that. And I wonder if you have had a chance to increase the soiling, and if there is any specifics on the spectral sensitivity of soiling, because soiling can affect different PV technologies differently. This is what we are saying in one of our projects. Mm-hmm. And so depending on the soiling type, we can have much higher than even 5%, even close to 10% here in Brazil at sites where you will have utility scale power plants. And also we are just getting started with this kind of study, but the spectral sensitivity of soiling. Do you have any experience on that?
We have somebody in our group who is our soiling expert, our dirt guy. So he could definitely answer this in more detail as well if you want to contact him later. Of course, I'd be very interested also to see any results that you have on these kind of soiling analyses here. There is obviously a spectral difference with the soiling as well. As we increase the levels of soiling, if you are seeing 5%, I think you will actually see a benefit for our modules. Again, not only because they're frameless, they may collect less dust, it'll slide or blow off very easily, but also if we have more soiling, that'll bring us below the clipping limit of our inverter, so we will see the full benefit then perhaps of our spectral and temperature advantages.
Okay, and one final question on the issue of the temperature coefficient. Over the years, going from series 2 to 4 now, your temperature coefficient has changed. It has slightly increased over time.
Slightly increased.
Can you tell a bit more about that?
It used to be 0.25, now it's 0.29. I can't go into too much detail. I'm not sure on what caused the increase, but we're still below typical mono and multicrystalline silicon modules, and you can see that for any temperature above 25 degrees C, we see a big advantage. And I've also been doing some testing looking at field data, and what we're measuring in the lab matches what we're seeing in utility scale plants very well.
Okay, one other issue here in Brazil is that we are getting started with distributed generation, so rooftop installations.
Right.
Do you have any experience on rooftop installations, temperature efficient effects on rooftop plants or small plants with your modules?
At this point, our rooftop team is still very small. We don't have enough data yet to start looking at temperature coefficient. We do have some test sites at our facilities in Arizona that are on the rooftop, but we haven't been able to measure that. Of course, we expect less cooling when you're on a roof mounted much closer.
Yeah, the benefit should be even higher than what you see at a utility scale plant. No more questions. So I think we'll break for lunch now, and if we can have a look at the lab, and then we'll come back after lunch.
Sure.
So, para quem está nos assistindo pela internet, nós vamos voltar a 1h30 com mais uma parte onde o Miguel vai estar falando sobre usinas de grande porte também. Então, por enquanto, muito obrigado e voltamos a 1h30.
And if anybody has additional questions that they think of later, feel free to contact me. I can give you my card or my email. And if you have specific questions regarding any of these technical concepts, our group is very active in publishing papers in different journals, so I would be happy to point you to those as well. So thank you guys for listening.